All right, as we start, what you're going to need for this lesson is on the board here. You're going to need from the document section of Sycamore Ed, you can go on there, and everything for week 1 will have week 1 written in front of it. I just abbreviated W1. But you're going to need week 1, the half-life calculations to go along with the lecture, week 1 half-life calculations practice, and those we're going to do together. And I will do a set of calculations that you don't even have. I would have a piece of paper and I'd write it down so you can look back at it. This is going to be kind of like math. It's going to look really easy when I'm doing it, but if you haven't tried it yet, then it's going to seem like it's rocket science, and it's really not. It's very simple. You're also going to need a periodic table. If you brought home, if you have the one that I gave you in class, that's great. Just get it out. If you didn't, there is a periodic table that you can also download, and if you can, print it out and just have it available on the document section as well. And it just says periodic table, and I think it says new. It's a little smaller, so it'll fit on a regular letter size sheet of paper, but it has all the same stuff. It actually has more significant digits on it, but you will need a periodic table. If you don't have one that's printed out, if you have on your phone or something, you can just look up. There's lots of images of periodic table there you're going to need. And then eventually you're going to need the week 1 half-life calculations that you're going to turn in. I'm not going to go over those with you now, but after we've done this practice, they should be very simple. And then week 1 radioactive decay of uranium-238, which you'll complete on your own. I'll get you started with it, so you might want to have that one available just so you can see what it looks like and make sure that you understand what it is. If you don't understand, remember, you can send me a pass-a-note, or on Thursday at 9 o'clock we have the Zoom time where you can go in and we can actually talk face-to-face, and you can ask me a question and I can answer in real time, and I can show you on a board how to do something if you haven't gotten it yet. So take advantage of that. That's not required, but if you have any questions, you can, or if you just want to get on and see pictures of your classmates and reconnect a little bit, that's on every Thursday at 9 o'clock. All right, so if you have those things, then we'll get started. If not, obviously you can just turn me off, pause me, and go get them and then start it up again. Okay, so the first thing we're going to do is half-life calculations, and the half-life of any radioisotope, any radioactive element, the half-life is the time required for half of it to decay. Now, radioisotopes don't decay like trees that fall down in the forest, and then you've got mushrooms and fungus that are growing on it, and animals chewing through it and breaking it down. Pretty soon it's dirt. Radioactive decay is different. You just have one element turning into another element because of the particles that are being given off. But if it's a rock, a piece of uranium, when you're done, it's still going to be a rock. It will take thousands and thousands of years, but at the end you'll have a rock, but it won't be uranium once it's all changed. It will be another element. We'll show you how that you can calculate what that is. But half-life just means the time it takes for half of it to decay, and that's going to be important in how we calculate this. And eventually, if you go on and, depending on how far you go in math, when you get to logarithms, there's actually a very complicated formula for calculating the amount left and the half-life of a sample using logarithms and exponents. But we're going to do the same thing. We'll just do it very simply, and so the numbers have to be nice and even, but we're actually doing the same in a lot different way. It's limited in what we can do, but for right now, you'll get the idea. All right, so a problem would be like this. If you have 2,080 grams of a substance, and it's buried for 10 years and it has a half-life of 2 years, how much is left? Some of you love story problems. I'm going to guess that's a small portion of you. I always thought they were more fun than actually just in algebra X and Y and doing that when you actually got to figure something out. But these aren't too bad. We're going to do all of them the same way. We're going to make a simple T-chart, so even if you have to pause the video, because you can always go back and look at it, but sometimes it's easier if you just at least write down the pertinent information, so later when you're doing your own, you can look back. Now, how did he do this? But we're going to make a simple T-chart, and on this side we're going to have time and amount, and you will see that as I go through I will just abbreviate that. I'm just going to put T and A here and just start by putting this down. When you see, oh, it's a half-life problem, just start with writing this. But one more thing, also put a 0 there. At time 0, how much do you have? If you forget to put the 0 and you start counting by half-lives over here, you're going to be off by one calculation. So we always have to start with 0. So this is what every time you start, your chart is going to look like this. Just write that down before you even go. I don't care what the numbers are yet. Put this down, and then we'll put the numbers in. So at time 0, it tells me that I have 2,080. That's at time 0. So I start with 2,080 grams at time 0, and it has a half-life of 2 years. On the time, I'm going to count up by the half-lives, which in this case is very simple. I'm going to count by 2s until I get to the total time, to 10. So this tells me what to count by. That's where I end. So 2, 4, 6, 8, 10. And from our definition, and I put those marks on there so I know that I'm going down the right numbers where I'm going. If you have lines on there, you don't really need it on the paper you're using. And the definition says that every time I go a half-life, I have half as much left. So as I go down here, I count plus the half-life as I go down. On this side, every time I go down one line, I'm going to divide by 2 because I only have half as much left. So 2,080 divided by 2 is 1040. And if I divide that by 2, I get 520. And if I divide that by 2, I get 260. And if I divide that by 2, I get 130. And if I divide that by 2, I get 65. So my answer for this, how much do I have left after 10 years? I started with almost 2,100 grams, and I only have 65 grams left in 10 years. Any questions? Almost have it. There might be, but we're going to do more practice. So you can, if you do have questions, you can go back and you can watch how I did that. Again, another one, and this is the one that most students, if they're going to have a trouble on one of them, it's the one that asks, what is the half-life? It's not really any different. It's just one more step that you have to do. So I see that it's a half-life problem. Time, amount, and 0, and now I'm ready to go. 10,000 tons were buried for 39 years, and 1,250 tons are left. What is the half-life? So I know at time 0, I started with 10,000 tons, and after 39 years, I'm looking for the half-life, so I don't know what I'm looking for what I count up. So I can't do anything on this side. All of these problems will give everything you need for one side or the other. This time I don't know the time side. Last time this is the side I knew and I had to calculate this one. This time I don't know this one. I'll calculate the amount. I'll calculate this. I know this side. It says I have 1,250 left. So I'm going to go down here until I get to 1,250. If I don't get to 1,250, that number doesn't come up, I'm going to go back and check my math here. But remember, on this side, I divide by 2 as I go down. So 10,000, half of that is 5,000. Half of that is 2,500. And half of that is 1,250, which is the number I look at. Sometimes a common mistake is students just keep going and they don't know when to stop. When do you stop? When this number matches this number. So I'm finished here. So I have to go down 1, 2, 3 half-lives. So I'm going to take the total time. It was buried for 39 years, divided by how many steps I have to go down, divided by 3 equals 13. So that should be my answer right there. The half-life is 13 years, but I'm going to check it. I'm going to pretend that I'm that math teacher, and you always check your problem. I should be able to count by 13s, and I should have 39 right here. So 0 plus 13 is 13, plus 13 is 26, plus 13 is 39, and I have the correct number. So this is my answer. 13 years is the half-life for this particular radioisotope. All right, now take out your, the part that goes with the lecture, the calculations that go with the lecture. There's 3 problems with that. And if you want to stop the video, pause it, and try and calculate those on your own, and then I'm going to go through and I'm going to solve them, and you can see where you got messed up if you didn't, or you can go through and, yep, I've got this. So we're going to do some more problems just to make sure you're comfortable with it. So depending on if you want to see me do 3 more, and then you still have 3 more to practice that you have before you get to the turn-in assignment. So if you want to just keep watching, otherwise pause the video before we go to the next part. It says if a 192-gram sample of a radioactive isotope has a half-life of 40 years, it's been buried for 160 years, how much of it is left? So I'm going to start with my same chart, put my 0 in, and at time 0 I had 192, and it's been buried for 160 years, so I'm going to have to get to 160, and I'm going to count by 40. So it's going to be plus 40 as I go down here, and I'm going to go to 160. You got to know when you're going to stop. And 80, and I can tell you that the most common mistake in this, because you did 40 and then it looks like you're doubling, and so you go right to 160, but you're adding 40. Students often forget this middle one here. Plus 40 is 120, and then I get to 160. Going across, I'm just going to divide by 2 as I go down on this side. So 192 divided by 2 is 96. Divided by 2 is 48. Divided by 2 is 24. Divided by 2 is 12. And this was grams. So my answer's in grams. And I don't know that I can't switch that. So my answer would be 12 grams after 160 years. Hopefully that makes sense. If not, you can go back and watch it and see exactly how I got that. problem 2, very similar, but asking it in a little different way. If a container is unearthed that contains 56 grams of a radioisotope, but the label says that there was originally 448, and the half-life of the isotope is 25 years, how long has it been buried? We haven't done one of these yet. Go ahead if you'd like to and pause the video, see if you can answer it first, and then check to see where it is or how far you can get at least. The important numbers that we need are going to be, we started with 448, we end up with 56 grams, and the half-life is 25 years. So I'm going to make my chart, time, amount, 0, and at time 0, I have 448 grams. And now I'm going to count down. I know what to count up by. I'm going to count up by plus 25 on this side. But I don't know how far to go yet because I don't know when I'm going to get to that. So I'm going to find the amount side first. I'm going to go down until I get to 56. And so half of this is 2, 2, 4. Half of that is 1, 1, 2. Half of that is 56. That's what I'm looking for. So now on this side, every time I go down, I'm going to count up by 25. So 0 plus 25 is 25, plus 25 is 50, plus 25 is 75. So my answer will be, that's years, will be 75 years. It would take 75 years for 448 of this to decay down to they only have 56 left. Now again, once you do this, it's not like we've thrown away the rest of the mass. It's just become something else, and some of it has, the particles have left, but we'll see in the next part of this that what those particles are that are leaving, how the mass is going away, but you still have a rock there. Just we have 56 grams of this left, and the rest of it has changed into something else. All right, one more, which is a half-life one. If 288 grams of a sample is buried for 200 years and only 9 grams remain, what is the half-life? So time, amount, 0. We start with, this goes at time 0, 288, and it's buried for 200 years, so I know I'm going to end up at 200 down here, but I don't know what to count up by. Here I don't know that again. And but I've only got 9 grams left after the 200 years. So I'm going to count down. I know everything on this side, so I'm going to count down here until I get to 9. That's the number that I'm looking for. So half of 288 is 144. Half of 144 is 72. Half of that is 36. Half of that is 18. And there's the 9 that I'm looking for. And this is grams. So that I have 9 grams left. And I know that this is at 200 years. So now to get there, I had to do 1, 2, 3, 4, 5 divisions, 5 drops down. 1, 2, 3, 4, 5. So I'm going to take 200 divided by 5, and that's going to give me 40. So 40 years, it is years, yes, will be my half-life. That's my answer, but I'm going to check it by counting by 40s to make sure that every time I go down, that I count up by 40, I should get to 200 right here. So 40, 80, 120, 160 plus 40 is 200. So I feel confident that that's the right answer. All right, now you should be able to take out the student practice and go through and answer those. And I'm going to come back here very shortly, and I will go through and work those with you as well. And then you can check to see if you've got them right. If you got those right, then you're ready to do the turn-in one. And that you can just download, keep it on a computer if you've got it there, and work it out on a piece of paper. Put the answers that you have on that paper, just type them in, and then you can just put it back in the Dropbox, and that assignment will be complete. There's just 3 questions, just like what is on your next practice assignment, just different numbers. All right, so give them a try. All right, hopefully you've had a chance to practice these. And again, you're going to need that practice sheet in front of you because this is going to be very hard for you to read. If a 192-gram sample of a radioactive isotope has a half-life of 20 years and buried for 120 years, how much is left? My time, amount, 0, 192, half-life of 20 years, buried for 120, so I have to write these fairly small, 20, 40, 60, 80, 100, 120. We're really going to need these lines. And going down, I get to divide them by 2, 96, 48, 24, 12, 6, 3. My answer, and this was grams, so my answer will be 3 grams. Make sure that you put a unit on the answer. Just the number 3 is not a measurement. Doesn't really tell me what it was. Make sure that you have the unit with that as well. So whatever I get here is going to go there. Second one, if a container is unearthed that contains 14 grams of a radioisotope, the label says that there were originally 448. Half-life of the isotope is 8 years. How long has it been buried? So again, time, amount, 0. And it starts with 448 grams. And the half-life is 8 years, and I want to know, so I'm going to do plus 8 going down here, but I want to go down until I only have 14 left. So on this side, half of that is 224, half of that is 112, half of that is 56, half of that is 28, that is 14, and that's what I am looking for. So I'm going to go down to here. So now I'm just going to count up by 8 till I get here, and whatever answer is in that box will be my answer. So I have 8, 16, 24, 32, 40. So it will be after 40 years that it has been buried that it would have only 14 grams left. All right, last one. Again, we're going to look for what is the half-life of the isotope, and I'm actually going to make my chart up above. It'll be easier for me to time amount 0. Start with 320. This is long enough. Maybe I will have to move it down there. 320, and I'm going to go till there's only 5 grams left. So 160, 80, 40, 20, 10. I'm going to wish I had been down here, and I'm going to drop down to 5. There, skip that number, so I've got to keep my lines going here. And this is at 42. And I've gone down 1, 2, 3, 4, 5, 6 times. So 42 divided by 6 equals 7. So it's 7 years. That should be my half-life. So I would say over here, 7, and they seem to put a 0.0, so I get 2 significant digits. Years, but I'm going to check it by counting up by 7s, and hopefully I get to 42 here. 7, 14, 21, 28, 35, and the next one is 42, and that's what I'm looking for. So I'm confident that the answer is 7 years. You are now ready to do your turn-in assignment. Just 3 more problems exactly like those. So you can go back and watch the video. You can look at any notes that you've taken, and it shouldn't be any problem. Again, if you do have questions, then I will be able to answer those, give you a push that you need on Zoom on Thursday at 9. All right. We have one more section to do on the radioactive decay series. So that's the part that you will need your periodic table for. If you want to stop this video now and actually answer those other questions while you just did these, just do it while it's fresh. That's probably a good idea. And then you can come back and get the rest of this when you're finished with that. All right, the next part going to be a radioactive series. When you have a radioactive element, it keeps decaying either by alpha or beta, and every time it gives off alpha or beta, it's going to give off some gamma as well. Remember, the gamma radiation is the part that's actually dangerous. That's the stuff that will give you the radiation sickness and the radiation disease and the burns and stuff. The alpha and the beta, they aren't good for you, but the alpha you can stop with a piece of paper, and if you're inside your house, your car, beta, you're protected from that. But both of them also give off the gamma rays, which are the dangerous part. And here's an example of decay. We start with plutonium, and I think I do this for you on the next slide. The plutonium, and as we write it, this says plutonium and 240 and 94. Remember, this is the atomic mass. Generally, it would be what's on the periodic table. The most common isotope of plutonium is plutonium-244, but this is a different radio isotope, is 240, but it's still plutonium because it has 94 protons in its nucleus, and down here's the atomic number. If you need that, you can write it in. It actually helps in what we're doing here, but we would know that that was 94 even if it wasn't there, because if it's plutonium, if you look on your periodic table, it's always going to be plutonium. And it gives off an alpha particle, and an alpha particle is, we wrote on your notebook in number 8, I'm sorry. In number 8, that it's really just a helium nucleus. 2 protons and 2 neutrons, which gives up 4 as a mass and 2 protons. So this gives off that, and when you do, then the plutonium changes into uranium. Now uranium, in this case 236, is still not stable, so it's going to move on to something else. And that's what a radioactive series is it just keeps giving off these particles until you come up with some element that is stable, and then the radiation stops. There's no more radioactivity. It's just we're now at a stable element. Until then, it'll just keep giving off more radiation. So if we do this one, it gives off plutonium 240. So it has and if you look on your periodic table, plutonium's atomic number is 94, and it gives off an alpha particle, and it gives off 2 protons and 2 neutrons. Each one of those has a mass of 1, so 2 plus 2, we're losing 4 from the mass, and we're losing 2 protons, so we're losing 2 from the bottom number. So every time you do an alpha decay, you're going to lose 4 from the top and 2 from the bottom. So if I take 240 minus 4, I get 236. And that doesn't identify anything. Many different elements can have a mass of 236. But if I have 94 protons, and I just lost 2 of them in this alpha particle that left, 94 minus 2 is 92. And now I can look if I can remember where I put it. There it is. If I look on, and you can look on your periodic table, here is plutonium. Here is plutonium, and it's number 94, but now it's changed into 92. So I'm going to look back at 92, and 92 is uranium. So we already knew that. They showed us that before. So it's now decayed into uranium. So every time there's an alpha decay, you're going to lose 4 from the top and 2 from the bottom. And you'll just write the top number, and then the bottom number, once you have it, you'll look on the periodic table, and that'll tell you what the new element is. So that's an alpha decay, always minus 4, minus 2. The beta decay is a little bit more interesting because we said that it is a high-speed electron from the nucleus, and the electron should be in the electron cloud. But remember, we talked about that a proton is just a proton. It's just a positive particle. But we said that a neutron is a proton with an electron attached to it. So that means that there is no charge now because we have the positive charge canceled by the negative charge that they have, but the mass is practically the same thing. For all the sig figs that we're going to use, they're the same thing because the electron has almost 0 mass. So small that we consider it to be 0 mass there. And then it makes sense because if we took, I think I have a couple of them here. If we took magnets and if we flip them so I've got them the same side, so it'd be like 2 charged particles have the same particle, and you put them together, they just want to push each other apart, and most of you have had fun doing that. It's kind of fun trying to push them together and feel this invisible force moving. Charges would do exactly the same thing. They're going to push apart. So how can we get all of these protons in, we just said uranium has 92 of them. How do we get all 92 of them to stay together? Uranium is radioactive, so they don't do it very well. But for the most part, they stay together. How do we? Because we've got neutrons in there that bring these electrons. So if we have a I can't make it. So you have all these positive charges, but if you have the right number of negative charges in between that act like the magnet's now flipped around, and you can stick them together. Now I could have another magnet here that is repulsed by this one, repelled by it, but if it's attracted to this one, it's still going to stick around. If you have the right number of neutrons that bring the right number of electrons in here, then it will be stable and it'll be there all the time. It won't be flying apart. But when we have beta decay, that means one of these gets shot out. So here we have a neutron, and then we have a beta decay, so this electron, did you really in the middle of this? All right, we have this electron gets shot out, and it's gone, and now all of a sudden our neutron has turned into a proton. So when we have beta decay, we lose an electron. So losing an electron changes the mass not at all, because we said the electrons have so small of a mass we consider it to be 0. So if it was 14, it's still going to be, whoops, it's still going to be 14. Hit the wrong one first. But we changed one of our neutrons into a proton, so we got one extra proton. So carbon on your periodic table is number 6. So that's what we would write down here if it was there. I did write it down, we don't really need it. You can just look on the periodic table. It's going to be number 6, but we're going to add 1 to it because we changed one of the neutrons into a proton, and it becomes 7. And if you look on your periodic table, number 7 is nitrogen. So in beta decay, carbon-14 changes into nitrogen-14. And this is the end of a series. That's the whole series. For carbon-14, we're done. Because if you look at nitrogen, its mass number underneath on your periodic table says 14.01. 14 is the most common. It's stable. That's why you take a deep breath, and you just took in mostly nitrogen-14. Very, very stable. So this would be the end, and there would be no next move here because that's where it's going to stay. Once you hit nitrogen-14, it's going to stay nitrogen-14. So in beta decay, the mass number doesn't change, but you add 1 to the atomic number, and you move 1 to the right on the table. In alpha decay, if you do alpha decay, it's going to lose 4 from the top, and you're going to move 2 to the left on the chart. So this is going to move you this direction 2 spots. Beta decay will move you that direction 1 spot. Now if you look at your radioactive decay of uranium-238, there's a bunch of steps as you go down. So it starts like this. You start with uranium-238, and it's number 92. So if I do an alpha, the first one is an alpha decay, so that's going to be -4 and -2. So 238 become -4 is 234. Be careful with this because you can see it's simple math, but that's the kind of math that we usually make. Oh, I can do this, and you just do it quickly, and you make a mistake. If you make a mistake on step 1 or 2, the chances of you accidentally correcting it somewhere, it's going to be wrong all the way down. So make sure that you take your time and go through each step carefully. 92 minus 2 is 90. Now look on your periodic table, and number 90 is thorium, named after some of your favorite Marvel character. So then we're going to start, for the next step is beta decay. So we're going to start with thorium-234, and we're going to give up a beta particle. Nothing happens to the mass, and we're going to add 1 here. So we get still 234 here, but 90 becomes 91. And then if you look on your periodic table, number 91 is protactinium. And then you will start, the next step would be starting with 234.91, and it's another beta decay. You figure out what it has, and that's where the next step is. So you just work your way through until you get to the end. The one that you end up with at the bottom should be a stable element. Now you're not going to know that it's a stable element, but I will know what it is. And if you can just, even if you just work out on a piece of paper and just put in that element that you get, I need at least the symbol, and I need the mass. Now, if you don't want to try and use superscript, it's not too bad in Word. Just if you click on the home part up there, underneath it, it has x squared, and it has x like this. You're just going to click on the one that looks like this in front of it and just put in whatever number. If you were going to do this one, you'd do 234, and then you would click out of it and put in the PA, and it goes that. But another way that's easier to write it, another way of writing this is just PA 234. Protactinium 234 is the same thing as writing it this way. This is isotopic notation. This is just the way we actually write it out. So if you give me the answer like that, that's fine. I'll know what it is. Now, if we were at the end and this was the right answer, and this is it, you would get the points. If it's not the right answer, it means you made some silly mistake somewhere. You subtracted 4 from the top and the bottom. Students do that quite a bit. And then you're going to be off by here. You're going to have the wrong, you might have the right mass, but you'll have the wrong element. And you want partial credit, which is fine. Take a picture of your sheet. As you write it out, take a picture of it, send that file and drop that into the Dropbox. And I will be able then to look at your whole sheet, and I can say, oh yeah, right here, they made the mistake right there. And if you just made the one mistake, then the rest of it would still be good. Then I can give you credit for all of it. I can just take a little bit off. If you just give me the answer, it's either plus everything or plus nothing, because I don't know where you went wrong. So you're probably better off sending me a picture of the sheet and putting it in the Dropbox. Hope that helped. If you have specific questions and you want to send me a pass-it note, you can do that. Otherwise, I can help you out on Thursday at 9. Also remember that you have a lab and a review sheet to complete this week, and turn those in before the end of the week next Friday. And then you will be completely caught up with the other class, and we will move on together next week.